I will shorten this part a little bit. Basically, what we are trying to do is to see what conditions have to be met to capture the wave modes which reflect at the eastern and western boundaries. So consider, let's say, a Kelvin wave of certain frequency propagating east, as we saw, can go at 2.5 meter per second or so in the Pacific, let's say typically during an El Nino, is going to hit the eastern boundary in about 3 months if it is turned on or generated at the dateline with this westerly wind burst that we talked about, which we will see again later. Then the reflection process requires that the frequency and cannot change, and the group velocity has to be westward because you want to move the energy away from the coast. And if the Kelvin wave is high frequency, then obviously that region where the gray region where you don't have westward group velocities cannot be met, the condition cannot be met, so you will just have fast inertial gravity waves being produced. But if you have a low frequency Kelvin wave of 30 to 40 day period, then you can have westward group velocities, but in the middle from week to 40 days, actually you can have Kelvin waves that deposit energy or pile up mass on the eastern boundary, and that propagates transversely along the coast as coastal Kelvin waves. Okay, that's all I will say. The math of that is in the book, but we don't need to go through those sorts of details. We'll just get to the physics when we get into ocean atmosphere solutions. But you understand how now the ocean has these low frequencies and the atmosphere can respond fast to changes in, let's say, ocean temperatures. So the atmosphere is always going to be almost in equilibrium with the ocean as the ocean changes slowly. So you can write the groups, the wave numbers in terms of frequency and gravitational wave speed, which is square root g prime h, let's say, where g prime is the reduced gravity and h is the thermocline depth. So that's our Kelvin wave. And for the mixed Rossby gravity waves, you have the beta term and the frequencies. And for other higher modes, we are going to have this complicated relation, and we'll see that to avoid this boundary reflection problem, one can make the so-called long wave approximation, which gives us reflection reliably at both the eastern and western boundaries. So Kelvin wave reflects as westward Rossby waves, and the Rossby waves at the western boundary can of course reflect as Kelvin waves because the group velocity is eastward. But there are also short Rossby waves which have group velocity eastward, but they don't propagate very fast, high frequency short waves, so they end up depositing energy at the coast as well and can generate coastal Kelvin waves. Okay, the western boundary intensification can in fact also be explained as Rossby waves bringing the energy, depositing the energy at the western boundary with short Rossby waves not able to get out, and then coastal Kelvin waves are generated, which can be actually detected, carefully filtered data, but the vorticity arguments and the beta effect is a much more solid and easy to comprehend explanation. So going to our wave equation that we had written in terms of the dispersion relation here with our refractive index written this way, we sought these wave modes, the real part of this with the longitudinal structure having this exponential form, and the meridional structure, as we saw, will come out to be Hermite polynomial. So in this case, The waves that are not possible are basically going to produce imaginary wave numbers, and you can solve for those and draw it in terms of the condition for which k, the zonal wave number, becomes complex in the lower limit and the upper limit related to this dispersion relation in that gray region between a period of about a week to 40 days. And that diagram looks this way. So you can generate inertial gravity waves and low frequency equatorial Rossby waves. In this region you have these imaginary wave numbers, but you have this solution running through here within the red contours where the real values of wave numbers are possible. So this region represents the real wave numbers. The wave number is complex, which means the westwardly exponential decaying solution is produced, which we don't want. So within these limits, energy is ducted away to higher latitudes as coastal Kelvin waves that transfer the energy to higher latitudes. Okay, so the frequency of the waves hitting the boundaries is going to determine whether you get slope waves along the coast, which we started with in the beginning, or you get reflected low frequency Rossby waves. Okay, I'm going to leave it there because these are very ideal solutions where we have assumed a stationary background state, which is not very realistic anyways. So let me leave this one here and do the long wave approximation in the next podcast, but I hope it's clear. We have Kelvin wave, Rossby wave solutions, as well as mixed Rossby gravity waves, inertial gravity waves, and Kelvin wave in the ocean. But the boundary reflections are a critical problem, and that produces specific constraints on which way the reflection happens, whether it's low frequency Rossby waves from the eastern boundary or short Rossby waves and Kelvin waves from the western boundary. Remember, Kelvin wave can only travel along the equator or along the coast. It needs a dynamic boundary on the right in the northern hemisphere, which means it has to go south on the western side, north on the eastern side, and it has to come down to the equator and then turn eastward. Okay, so all those kind of intuitive things you have to make sure you understand. So short Rossby waves cannot go too far because they get, in fact, Doppler shifted. They end up depositing the energy at the western boundary and produce Kelvin wave or slope wave. On the eastern boundary, when the frequencies don't allow low frequency westward group velocity, then the energy is deposited and creates slope waves which go northward. Of course, the whole thing reverses in the southern hemisphere. Okay, during an El Nino, we'll see that in fact coastal Kelvin waves can go all the way into Gulf of Alaska, and they can propagate as Rossby waves away from the coast at low enough frequency that it takes them a decade or so to cross the Pacific at northern latitudes, and they can come back to the tropics as coastal Kelvin waves. So you can imagine the whole loop. Okay, cute stuff. Make sure you understand it.